Good morning. So, my name is Michael. I work for Kienvolk. We are a small company from Berlin. We do mostly Linux software, and among many other things, it's eBPF today. So the talk is about gobpf. It's a fairly new library to work with eBPF programs from Go, and it aims to help you to access the eBPF subsystem from your Go software. The talk is basically two parts. It's the first part on eBPF in general, so what is it, how does it work, the basic principles behind it, and in the second part we are going to look into gobpf, which is also split into two parts depending on what your use case is, and yeah, just see how it works in general. So eBPF is a so-called bytecode virtual machine in the Linux kernel. Today it's used for tracing, networking, so software-defined networking, for performance analysis, for security purposes, and so on. The classic eBPF, or the Berkeley packet filter, is much older, so the functionality to use it for packet filtering has been in the Linux kernel for a long time, and it's used by, for example, TCP dump. In 1992, there was no unified way to filter network traffic, and the BSD packet filter paper brought such a system, which then was implemented for the Linux kernel as well. And today it's called enhanced BPF because it has grown a lot more functionality over the usual packet filtering use case. You can attach to kernel events. You can modify network packets, or to drop them, or to route them. You can use it to do syscall filtering and a lot more stuff. A nice property is the safety guarantee you get through the BPF verifier. So when you load your BPF program into the Linux kernel, it first gets verified because the kernel needs to make sure that your program isn't malicious, it doesn't block the kernel forever, and so on. So after your tool gets through the verifier, you can be sure that there are no loops in there, that there is no invalid memory access, and so on. And of course, you are running in the kernel, so it's very fast, and it's also JIT compiled on some architectures. So yeah, fast is a requirement to do, for example, networking, so it's good we have that. So from a high-level perspective, it looks like this. In user space, you have your program, and from there you use the BPF syscall or some library which makes your life easier to interact with the Linux kernel and load your program or your programs. You can have many of them. Those live in kernel space, of course. And then you have eBPF maps to share data between eBPF programs and to share data between the eBPF program in kernel space and your program running in user space. So first, a couple of details on eBPF programs. They can be attached to sockets. That is, again, the traditional use case. If you want to execute some eBPF program whenever a packet arrives, you can use that feature. You can attach to kernel trace points. The Linux kernel already does define a lot of trace points, so you often you can just look into what you want to trace. You can check out the kernel source tree, see where the trace points are, what is available there, and then maybe just attach to a trace point. If that doesn't work for you, kprobes maybe do. You can use kprobes to inject a program as a handler at a certain address. So for example, if you want to trace a syscall, a Linux syscall, you could use a kprobe, which then always triggers when the syscall is executed. And there are uprobes. That's basically the same as kprobes. The only difference is that those are for user space function calls. So if you want to trace something there, you would use uprobes. Then we have maps. Maps are the data structures to share data between kernel and user space. When you create a map, you can say what data you want to put in there. So it's up to you if you want to have an integer value in there and you only need to store one, you can create a map with size 1 and define that key and value is of type integer, for example. And there's one special map. It's called proc array. And this is sort of a lookup table in the eBPF system, which contains entries to other BPF functions. So if you want to replace your currently running eBPF program with another one, you could look up one there and call it. And you should be aware that the main page for BPF is rather out of date, so it can be pretty hard to get information on the available programs or map types, and you should look into the source code. So I think right now maybe 4 map types are in the main page, and in Linux 4.10 are 8 or 10 map types, so it's not super up to date. Yeah, that's the list of existing maps right now. We have a hash, which actually works like you would expect from a hash or a map key value. We have an array, and then we have different types for special use cases. I will show you one in detail, and that is type perf event array. So it's an array of file descriptors with perf event data, and the nice thing about it is that the kernel can just write into a ring buffer and doesn't have to wait for you in user space, and the user space program can then map the memory of the ring buffer and read from it asynchronously. And that's also a type of map that you often would use when you use kprobes to trace something, and we will see that in one example later. So to give you an idea how BPF looks like when you really write a BPF assembly or pseudo-assembly, I will show you a short code snippet, but you don't usually have to do that. So that's a very small program you could load into the kernel as is to count fjoin at syscalls. So whenever the syscall gets called, it increments the counter by 1 and exits. And yeah, as you can see, it looks rather tricky and it's not very approachable. So fortunately, we don't have to do that, but we can use tooling. Around enhanced BPF and modern tracing tools on Linux, there is the IOVisor project. You can find it on GitHub and also on iovisor.org. So if you are into that and want to learn more about the available tools, find documentation and so on, that's a good place to start. So now on gobpf, it's, as said before, a library to create, load, and use eBPF programs, and it's actually two sub-packages. It's one which allows you to use CGO and the BPF compiler collection, and a second package which allows you to use pre-built ELF object files, and we will have a quick look on both parts. Why gobpf? When we started working in that area, there was no library yet which did what we wanted to do, but we found the Hoover project from IOVisor, which wants to be they call it data plane. So I think the idea is that you have a daemon on your system, and then you ask the daemon via an API for system data, and the program then loads, for example, some eBPF program to provide you with the necessary data. And second reason is we work on weavescope, which is a tool to do cluster monitoring, so for example Kubernetes, and this is written in Go, and it also needs to gather a lot of data from your system, so for example running processes, containers, network connections, and right now their approach is to parse proc and check the contract tables, and this is rather difficult to do because you have to scan a lot of data, and that very fast, and when you have a lot of processes or a lot of containers, it can be tricky to do that reliable and fast. And depending on the use case, it's much nicer to have eBPF there, because the kernel is doing a lot of work, and you just have to read the events then. So when you use the BCC package from gobpf, you can write your program in C. It's a modified C language for BPF backends, so it feels like C. You have to be careful about a couple of constraints, because in the end, the BCC will build an eBPF tool out of it, and it has to pass the kernel verifier. But it makes things a lot easier. You have a lot of helper functions. Interacting with a map is much more comfortable than the assembly code we saw before, and so on. libbcc actually is not only the library which helps you to write your program, but it's also a compiler. So it works like you pass it your program as source code. Either you read it from a file, or you just have it in your Go code in some constant, for example. And then it translates your program into BPF bytecode. So we can actually verify it, or BCC verifies it for you before it gets passed to the kernel. And BCC also provides you with a lot of headers. Before, you often had to import kernel headers to have all the necessary definitions for BPF, and all that is in BCC. So it's really a nice library, and you should check it out if you want. So I will show you a bit of source code. This is a snippet from the example tool in the gobpf repository, and as you can see here, we just define a source variable and put our C code in there. Two important things here. One is we define a struct of type chown event, and then we define an array, and it's of type perf event, as we saw before, where we are going to write those events. So that's the map which we then can read from user space later. And the Go part looks like this. Here we load the source code, then we get a reference on the table, then we get a reference as a perf map, and we pass it a channel, and then we can read from the channel the events. So we have a loop, we just wait for data, and whenever there is data, we print it. And in gobpf BCC, it looks like this. We open a perf buffer, and we give it a callback cookie, and then we have a gateway function which takes the cookie, looks up the handler data, and sends back the event data. So I will quickly show that to you. So here we have the example program, and since you need root permissions for the BPF syscall, I am root here. And when I now do some action here, you can see we get an event, and we get correct reports on what was happening and also the return value. So I was not allowed to do the second operation, permission denied, and here is the return value, not 0. Yeah, so the second package in gobpf is elf. So if you don't want to translate your program before you actually use it, or if you cannot ship the libbcc on all your systems because maybe it's too large and your containers should be small and tiny, then you could think about using precompiled object files. This feature relies on ELF sections. So in Linux ELF files, you have sections. And by setting particular section names, so here, for example, kretprobe for a return probe, we allow gobpf to detect from the ELF file how the contents should be loaded. If you are interested in that, you could have a look on the TCP tracer BPF package from Weaveworks. It's, as the name says, a TCP tracer. And we plan to use that in scope. So it does exactly that. It's a very small C program. It gets compiled to an ELF object file, and we then later load it with gobpf to trace TCP connections. Yeah, you can create such object files with Clang. I think the BPF backend has been in the static compiler for quite some while. So you first produce bitcode object file and feed that into the compiler, and then by selecting architecture BPF, you generate the BPF bytecode for later use. A nice or tricky feature of gobpf ELF is that you can create your program for multiple kernel versions. Usually you have to tell the kernel when you load a program for which version it was written, because the kernel will only accept a program which was written exactly for the version you are running. And this can be tricky when you have a patch release of the Linux kernel. You maybe don't want to recompile your program. So we built in this feature, when you set it to this constant, we will try to guess the current kernel version during runtime, and then just say to the kernel, yeah, we built it for that version. You can do that. It can be tricky because sometimes kernel structures change, functions change. So depending on what you do in your eBPF program, it could break afterwards. So you should know what you can expect from the kernel or what you rely on. And one last word, continuous integration is also tricky. you need root access, you need a modern kernel, you often don't have that, so if you ever need to test Linux kernel features, have a look on Stage 1 Builder, on the Stage 1 Builder project. Here we use Rocket for custom, we use Rocket with a custom Stage 1 image, which allows us to test any workloads on CI systems. And time is up, I believe, so that's it. Thanks.
We have time for a question because Ron needs some time to build up. Anyone having a question? Yeah.
Yeah, actually, I have two questions. First, I didn't get the main idea behind using eBPF in the context of tracing, as it's firstly used in networking, especially for filtering packets. So what are the new features that give it this good reputation? Second, in the context of tracing, what about its overhead compared to other root tracing tools like Datras or System Tab, and how we can measure it? Thank you.
So I think I will start with the second question. So I think the main feature, the main advantage here is that you now can have it in mainline kernel. You don't need to have any extra modules. It's supported by upstream. Yeah, and regarding the first question, so a lot of the functionality wasn't possible before, so maybe you know Brandon Gregg from Netflix, who has been doing this for a long time, and dtrace from Solaris always was quite powerful to trace systems, and Linux for a long time didn't give you the same features to trace programs. Regarding networking, one feature from eBPF is fast data path, XDP. It's used, for example, by the Cilium project. So they do container security and networking with eBPF, and this is something you couldn't do before. And, yeah.
Any other questions? No? Okay. Thank you very much.